Good morning to all. Myself Dr. K. Manoharan, Associate Professor, Department of Biomedical Engineering. So today class we are going to discuss about bilinear transformation method of designing an IR filter. So analog filter we can use in any method, that is a Butterworth or Chebyshev filter. After that we are going to convert into a digital filter by using this bilinear method. Look at this given problem is using bilinear transformation, design a high pass filter monotonic in passband with a cutoff frequency of 1000 Hz and down 10 dB at a frequency of 350 Hz. The sampling frequency given is the 5000 Hz. First we can write the given specification. So alpha p, so that will be 3 dB. So this is the maximum possible attenuation. And then omega c, that is equal to omega p equal to 2 pi into, they given as a 1000 Hz, so into 1000, so that will be equal to 2000 pi radians per second. And alpha is the minimum they said is a 10 dB. So this is omega s equal to 10 dB, and then omega s will be equal to 2 pi into fs. So this is an alpha s is 10 dB and omega s equal to 2 pi into 350 Hz, that will be 700 pi radians per second. So sampling rate they given as t is equal to 1 by f, that is equal to 1 divided by 5000, that is equal to 2 into 10 power minus 4 seconds. They asked to design a high pass filter, so we need to map this high pass filter specification into a normalized low pass filter specification. Look at this, this is the given specification. So minus 3 dB at the frequency as omega p is 2 to this is the given value minus 3 dB and this is the minus 10 dB values. So this is omega p and this is omega s. Similarly, so this is mapped to low pass filter, the same attenuation. So only change is omega p becomes omega s and omega s becomes omega p. This is the only change. So alpha p alpha s, there is no changes. Omega p omega s only changes. This because low pass and high pass is just opposite. Low pass filter content, there is low frequency will be pass band and high frequency will be stop band. If you take a high pass filter, just opposite, high frequency will be pass band and low frequency will be stop band. So the only change is omega p becomes omega s and omega s becomes omega p. Look at this. So I am going to find a pre-warping frequencies. So pre-warping we need to use this omega p omega s equal to 2 by t into tan of omega p by t into 2. So this symbol indicates an analog filter. This symbol indicates a digital filter frequencies. So that will be equal to 2 divided by 2 into 10 power minus 4. This is a sampling frequency. This is 2 by t and tan of 2000 pi into 2 into 10 power minus 4 divided by 2. So that will be equal to 7265 radians per second. Similarly, omega s I am taking this, so substituting here, so 2 by t into tan of omega s by t by 2 into that value. So that is 2 divided by 2 power 10 power minus 4 tan of 700 pi into 2 into 10 power minus 4 divided by 2, that will be equal to 2235 radians per second. So this is omega s and this is omega p. So this value only written here. Look at this omega p and this omega s. So here this omega p becomes omega s here, this omega s becomes omega p here. Now we can use the low pass filter specification to design a filter. After that we need to convert it a high pass filter. We know the filter things. So for designing a low pass filter from the given specification, use suitable transformation, obtain the transfer function of high pass filter. That is the graph transformations. N equal to log of 10 power 0.1 alpha s divided by 10 power 0.1 alpha p minus 1. So divided by log of omega s by omega p. So here we need to use omega s omega p as a low pass filter specification because we are going to design only a low pass filter in this step. After that only we are going to convert it a high pass filter. So use this low pass filter specification, substitute the values. From that I am getting that n equal to 0.932. So from this I can write it n equal to 1 because this is 0.932 no, so n equal to 1. So for n equal to 1 we refer a table and then write a h of s. So 1 divided by denominator function, that is equal to 1 divided by 1 plus s. So this is the low pass filter function. Now we need to convert it into high pass filter function with the given specifications. So omega c equal to 7265 radians per second. So s should be replaced by omega c by s. So in low pass filter normally we replace s by omega c. In high pass filter we need to replace omega c by s, just opposite. So omega c equal to 7265. So we replace s should be equal to 7265 by s. So h of s equal to 1 divided by s plus 1. So s should be replaced. So 1 divided by 7265 5 divided by s plus 1. So cross multiplying it and common denominator, that s is bring to numerator. So it becomes s divided by s plus 7265. This is the transfer function of high pass filter. Now we are going to make it is a digital filter. So for a digital filter, we know that h of z equal to h of s, where s should be replaced by 2 by t into 1 minus z inverse divided by 1 plus z inverse. Now we are going to replace it. Look at this, s divided by s plus 7265, where s is replaced by 2 by t value is 2 into 10 power minus 4 into 1 minus z inverse divided by 1 plus z inverse. So that is equal to 10,000 into 1 minus z inverse divided by 1 plus z inverse. Similar denominator also 10,000 into 1 minus z inverse divided by 1 plus z inverse plus 7265. So this value we are substituting it. Again, after simplification, we need to take this denominator as a common, that 10,000, and need to make it a numerator. That's why I am getting the value 0.5792 into 1 minus z inverse whole divided by 1 minus 0.1584 z power minus 1. Thank you.